And we are back. Sorry about the interruption, but we left off in the middle of the problem here, where we're taking, so the reaction's 35% complete, so that means 65% of it is unreacted. So we're taking the natural log of that concentration, what's left, 65% or 0.65. We're solving for K. The time here is 55 minutes. And then the concentration at time zero, the reaction hasn't occurred yet, so it's 100% unreacted, or if we're converting that to decimal form, 1. And always the natural log of 1 is 0, so if we're adding 0 plus anything, we can ignore it. Okay, so here that means we're taking the natural log of 0.65, dividing by negative 55 minutes, so that means K, this rate constant, is 0.0078, and keep in mind the natural log of 0.65 is negative, dividing by negative 55. This rate constant will always be positive. And now the units here are inverse minutes. Okay, so that's using the integrated rate law for first order reactions. And now to identify if something's second order, so this is our differential rate law, or just the rate law. So that reactant to the second power, so that means, remember, for the second order reactions, if you double concentration, that quadruples reaction rate. Or if we were to triple concentration, that would increase the rate by a factor of 9 times. So now how we write the integrated rate law, how that rate is dependent upon concentration and time, is the following. Instead of natural log of that concentration, now it's in terms of the inverse concentration. So you just have to be careful. Remember, it's inverse concentration and not concentration. So same thing, we can plot this using a graph, y equals mx plus b. So if you plot inverse concentration, the y-axis, versus time, the slope will now be positive k, and then the y-intercept will be the inverse concentration when time is 0. So with the following, if you do this graph, and you should be able to graph some simple values on your calculator, if you plot natural log versus time, you find, okay, that's not a straight line. That means that reaction cannot be first order. Then you try, okay, maybe it's second order. So you plot inverse concentration versus time. That is a straight line. Therefore, this reaction is second order, with the slope being equivalent to that rate constant. And just like we did for first order, we can solve for the half-life of this reaction. Whereas first order, the half-life was constant. It was independent of concentration. Here, half-life is dependent on concentration, and it's inversely related to concentration, meaning the half-life gets longer as the reaction progresses. Okay, because the concentration, as you go throughout the reaction, the concentrations of the reactants gets lower and lower and lower, because for each successive half-life, the initial concentration is halved each half-life. So that means the half-life of a given reaction is doubled the preceding one. So if this is halved, that means the actual half-life is doubled each preceding time. Okay, so now if you're given this, you should be able to identify, okay, is this a first order or second order reaction? So you're given the first two half-lives are 25 and 50 minutes respectively. So that means it cannot be first order since those half-lives are not constant. If you look here, 25 to 50, that half-life is doubling, meaning it has to be a second order reaction. So if we want to know the rate law, When it's asking for the rate law, that means the differential rate law, so that means rate equals k, a to the second power, since it is a second order reaction, since the half-lives double. Okay, now if we want to calculate k for this first part, we know that k, if we rearrange this equation for half-life, if we arrange this for k, we get k is equivalent to 1 over T1/2 times initial concentration. So we know the first half-life here is 25 minutes, and the concentration at time 0 is 5 molar. So that means here, once we do all that, we get a final rate constant of k of 0.008, and since these are both in the denominator, we have to invert them. So that means our final units of k are liters over minutes times moles. Okay, then finally, if we have to calculate the concentration when the time's not a factor of the unit of a half-life, that means we have to use the integrated rate law for the second order reaction. So that means here the integrated rate law for the second order reaction is as follows. Okay, so we're trying to calculate for concentration of A. Now we know K, we just calculated 8.0 times 10 to the negative third, or 0.008. The time given to us in the problem is 525 minutes. And then it's adding the inverse of the initial concentration, which is 1 over 5 molar. Okay, so now when we do all that, and remember, you can't just stop and calculate all this out. This is all equal to inverse of concentration. So once you get your answer, you have to take the inverse of that. So the final concentration you should get of A is 0.23 molar. Okay, so that's how you use the integrated rate law for second order. Finally, for zero order, and remember, for a zero order reaction, the rate is constant. It does not depend on concentration. So it's this A to the zero power, which is just 1. So always for zero order reactions, rate is just equal to K. Okay, so that's for the differential rate law, how rate is dependent on concentration. Now for the integrated rate law, how concentration and time affect the rate, and we plot this out. If we plot simply concentration on the y-axis versus time, our slope here will be negative k. So if you do that, and it gives a straight line, and that slope will be negative k, you don't need to plot anything else. And finally, for zero order reactions, it's half-life. So here, it's directly dependent upon concentration of the reactants, and so the half-life over the course of the reaction will decrease because the concentration of the reactants decreases over time. So that means the half-life gets shorter as the reaction progresses and the concentration of the reactants decrease. Okay, so you should be able to tell the difference between zero, first, and second order rate laws from their graphs. Remember, zero order, it's simply concentration versus time is a straight line with negative slope, rate constant k, negative k. So zero, you do concentration versus time is a straight line, and that slope is negative k. For first order, it's the natural log of the concentration versus time that will yield a straight line, with that negative slope being the negative of the rate constant. Then finally, second order, it's the inverse of the concentration versus time that will yield a straight line. And for this one, that slope, that straight line, is k. Okay, so when given a set of values, you should be able to identify what order it is. Okay, and always, so you should be able to identify these parts on your own. But for all of these, so you should be able to graph that, determine if it's zero, first, or second order. But for all these, you'll be given these integrated rate laws as well as the half-lives for any quiz or test, so you do not have to memorize those equations. You should be able to come up with a rate law on your own and then figure out via a graph what order the reaction is, but you will be given all these equations to work with those. Okay, and you should be able to use all those equations, if it's zero, first, or second order, to calculate some concentration after a certain amount of time has passed. So for example here, if this is zero order, we know our integrated rate law for zero order is this. So that means here the concentration of A is equal to negative KT and usually here for zero order the units of K are the same as they are for rate, moles over liters times seconds. The time here, 30 seconds. And then we add it to the original concentration of A. And when you do all that, you get a concentration of A is 4.7 molar. Okay, then when we do the same thing for first order, so now, since we know it's first order, we know it's the natural log of A. That's what we're solving for. Okay, so the natural log of A, that's equal to negative KT. And here, for a first order reaction, remember the units of K will be some inverse time. So our unit of time here is seconds, so inverse seconds times 30 seconds. And now we're adding the natural log of our initial concentration, which is 5 molar. Okay, when we do all that and we solve for the concentration of A, our concentration of A is 3.7 molar. Okay, and then finally, if we do the same thing for second order, so it's telling us it's second order, so that means we use the integrated rate law for second order, where its inverse concentration is equal to KT plus the inverse of the original concentration. So that means it's equal to 1.0 times 10 to the negative second. And here, that means those units of time is inverse molarity times seconds, and then times the time and the inverse of the initial concentration. So inverse 5 molar. Then finally, once we do all that, for inverse concentration, it's equal to 0.5, but we don't just stop there. We want the actual concentration of A, so the inverse of 0.5, 1 over 0.5, that final concentration of A is 2. And if you'll notice, all of these values make sense. They're all less than the original concentration of 5, and always the reactant concentration will go down and decrease. Okay, so that's the integrated rate laws of 0, first, and second order. You should be able to solve for those and solve for each of their half-lives. All right, that's all for today. See you next time.